4.3.2 Junction conditions. Now that we know the Maxwell equations that govern in a given macroscopic body or medium, we can speak of having different media and of the interfaces between those media. In other words, what are the junction conditions indicated by Maxwell's equations, being valid in both regions and at the interface of those regions? This sets up what is known as the pillbox formulation of the boundary conditions, where we go from differential to integral form in Maxwell's equations using vector integral calculus, and 2, we set up a pillbox volume that straddles the two regions encompassing the interface between them with a simple to the surface comprising the vertical dimension of a very short pillbox at the interface between the regions. Maxwell's equations in integral form.
Equation 4-43. Equation 4-44. Equation 4-45. Equation 4-46. The boundary conditions at interfaces between different media with appropriate choice of pillbox. See the next equation. Equations 4-47. Where sigma is surface density and K is surface current. A final complication is then for the case of a moving boundary, V equals C beta. This is described in P. D. Nordlinger, A.M. J. Physics 39, 191, 1971, where we find that I and the second hold without modification, where sigma is surface density as observed in the laboratory. In determining 3 and 4, we can no longer ignore the time derivative terms. So let's go to the comoving frame of the interface where we have
Equation 4-48a, since the convective derivative is 0. Equation 4-48b. Upon substitution, along with use of a vector calculus relation from section 4.2, we thus have equation 4-49. Thus, we find after some reworking, equation 4-50. In the simplest case where D equals E and H equals B, we get
equation 4-51, which is clearly exhibiting a correction at second order in beta. So, as long as we are considering boundaries moving at non-relativistic speeds only, then there is no correction to the simple pillbox boundary analysis. Likewise, as long as we aren't considering exotic ferromagnetic matter, atomic matter, or neutron stars, or any star, then we have simple diamagnetic and dielectric coefficients. This is the focus of the standard applications of Maxwell's equations in this chapter. This is the majority of applications that aren't of an astrophysics research nature. Relativistic magnetohydrodynamic considerations will be briefly considered in Book 3, when much of the math and physics has been covered for other reasons. Let's now turn to the junction condition issues that can specifically arise in the electrostatic case. For this we will concern ourselves with surface distributions of charges, dipoles, and the possibility of discontinuities in field and potential. This is the first encounter with special functions and their well-definedness by way of distribution theory, not yet invented at the time Dirac introduced the delta function in what follows.
Consider a surface with a charge density sigma. Equation 4-52. Let's now consider what's known as a dipole layer, where we have charge densities on parallel surfaces, d apart, and with surface charge plus or minus sigma. What potential is produced by a dipole layer? Equation 4-53. Since we are dealing with a distance d to be made arbitrarily small, we can make use of a Taylor expansion.
Equation 4-54. To get at first order in d, phi of x equals the integral from s to of sigma of x prime over the absolute value of x minus x prime d of a prime minus the integral from s prime to of sigma of x times open brace 1 over the absolute value of x minus x prime plus n d of x dot gradient 1 over the absolute value of x minus x prime close brace times d of a double prime. Equation 4-55. Let's introduce surface dipole moment density d of x prime equals sigma of x prime d of x prime.
Equation 4-56. Thus, the potential at x caused by a point dipole at x prime is equation 4-57. Since negative n dot gradient 1 over the absolute value of x minus x prime times dA prime equals negative the cosine of theta dA prime over the absolute value of x minus x prime squared equals negative d omega. Equation 4-58. We can also write phi of x equals negative the integral from s2 of d of x prime d omega, equation, for dash 59, where d omega has positive sign if the angle is acute, i.e., when the observation point views the inner, negatively charged side of the dipole layer. For a constant surface dipole moment density d, the potential is the product of the moment and the solid angle subtended at the observation point by the surface regardless of shape. Consider what this means for the potential seen upon crossing a charged double layer. Just under the double layer we have inner surface subtending 2 pi solid angle half, so potential is negative 2 pi d, on the outer side we have 2 pi d, thus the potential step seen when crossing the surface is
equation 4-60. Let's now consider the Poisson equation, with source, and Laplace equation, no source, from this perspective. Thus, from gradient E equals 4 pi rho and E equals negative gradient phi we have gradient squared phi equals 4 pi rho, Poisson's equation, and if no charge is present, then gradient squared phi equals 0, Laplace's equation. Notice the oddity that gradient squared 1 over r equals 0 for r is not equal to 0 while its volume integral is negative 4 pi, which was managed by Dirac with introduction of the Dirac delta function delta of x.
Equation 4-61. Thus, we see the distribution theory elements of the step function theta of x and the delta function delta of x. In what follows, the differential expressions involving discontinuous functions can always be expressed in terms of their integral forms, where those discontinuities have well-defined evaluation. Thus, the integral transforms due to the divergence theorem and integration by parts are critical tools in applying the theory. To this end, early developments were done by Green, whose theorems thus follow as simple applications of the divergence theorem.
Equation 4-62. Where Green introduces. Equation 4-63. Green's first identity is then. Equation 4-64. And Green's second identity is. Equation 4-65. The general form of Green's function to be introduced is based on generalizing the interesting form that results when we use Green's second identity with 1 over r equals 1 over the absolute value of x minus x prime, which gives gradient squared psi equals negative 4 pi delta, where delta equals delta times x minus x prime is the delta function. And we also choose phi equals phi where we have gradient squared phi equals negative 4 pi rho.
Equation 4-66. As s goes to infinity we get the usual result that phi equals the integral from v2 of rho over r d cubed x prime, but for the boundary surface not at infinity we have a form that makes clear that two types of terms exist at the surface boundary, that relate to Dirichlet and Newman boundary conditions in what follows. Note, if the reference coordinate x is not inside the boundary surface in the volume V, then we have
Equation 4-67. Green's analysis then goes further to consider the general Green's function that has form. Equation 4-68. Where g of x prime bold equals 1 over the absolute value of x minus x prime plus f of x prime and gradient prime squared f of x prime equals 0. Equation 4-69. And we are free to choose f of x prime to eliminate one of the surface terms, e.g., use Dirichlet or Newman boundary conditions. We know that we can write
Equation 4-70. And with Dirichlet b cease. G sub d of x prime equals 0 for x prime on S and we get the form. Equation 4-71. For Newman b cease we can't similarly choose partial derivative of g sub n with respect to n equals 0 as this is too restrictive. To find the simplest allowable BC on g sub n start with the form gradient prime squared g sub n of x prime equals 4 pi times delta times x minus x prime and use Gauss's theorem to get the relation.
Equation 4-72. The simplest BC is then Equation 4-73, where the absolute value of S is the total area of the boundary, and we get the relation. Equation 4-74. In this process, the freedom to choose f of x prime to zero out boundary terms at a surface is equivalent to the freedom to choose a system of charges external to the volume to achieve that BC. This is equivalent to using the method of images. Note that the Green's function approach works with respect to ODEs using any division algebra, thus can extend to quaternion and octonion formulations, as well as complex.